Hello everyone. In this video, I'm going to be going over solving systems of differential equations by a process called systematic elimination. I'm just going to go over a few examples. So you have in each of these examples there are two dependent variables, x and y, and they both depend on an independent variable, t. And we're trying to find functions x of t and y of t that satisfy every equation in the system. And what you're going to see is that solving a system of differential equations through systematic elimination starts off in a very similar fashion to solving a system of linear equations in algebra, like beginning algebra, through the elimination process. So hopefully you'll see what I mean when we get into these examples. Alright, so in my first example, again, I have the same instructions for all. I'm going to go over 3 of these. Solve the given system of differential equations by systematic elimination. So again, I'm trying to find, in all 3 examples, I'm trying to find 2 functions. A function x that depends on t, and a function y that depends on t that satisfy the system, right? Both equations in the system satisfy system. Okay. So this first equation, this first system is 2 equations. So the derivative of x with respect to t equals 2 times x minus y, and the derivative of y with respect to t equals x. So what I'm going to do, and what will make solving systems such as this easier, is write them using a linear differential operator, d, where d represents the derivative of something with respect to t, the independent variable t. So the system looks like this now. Right, so dx dt is just going to be relabeled as d, almost like d times x, or the operator d applied to x, equals 2x minus y. And this second equation, this dy dt, that's the operator d applied to y. So again, it looks like dy or d times y, even though it means, take the derivative of y with respect to t. And this equals x. And then just as you would in a basic algebra class, intermediate algebra, I'm going to take all the terms with the variables, the dependent variables, to one side, and terms with the independent variables on the other. Now there are no terms with dependent solely on t here. So I take all the x's to one side, and y's to one side, and then constants on the other. So you have dx minus 2x, and treating these like polynomials here, this will be the quantity d minus 2, the operator d minus 2 times x. So this is saying, take the derivative of x and then subtract 2 of x. That's what I've done. Right? But put them together as they both have x in common. And then plus y equals 0. And then, we have minus x, right, subtracting x, and then plus the derivative of y, dy, with respect to t, equals 0. So I line up the x's, line up the y's, just as you would with a system of linear equations back in algebra. And then, pick a variable to eliminate. Which one do you want to eliminate, x or y? So say I wish to eliminate y. Right? Say I wish to eliminate y. Well, that means I need them to have the same, coefficient, the same operator. Well, technically opposite operators in front of them. And then I'll add the equations together, just like, again, very similar to how elimination worked back in regular algebra. So what I'm going to do is, see, I've got this differential operator d in front of the y down here. I'm going to apply d to both sides of this first equation. That'll give me the dy there. I'll also have a d on this, and then the derivative of 0 with respect to t is still 0. Then they'll both have dy, and then, just to make sure that they're opposites, I'll multiply the second equation by -1. Everything. So let's see what that gives me. Alright, so again, the first equation, you have, d is applied to every single term. So now I have d times d minus 2 times x, or of x, plus, and then d applied to y equals, and then d applied to 0 is still 0. Right? The derivative of 0 with respect to t would still be 0. And then multiplying the second equation by -1, I get x, positive 1x, minus dy equals 0 times -1 is 0. And now, the coefficients or the operators on y are opposites. So then we add the equations together, and then when we do this, right, add both sides of the equations, just like in elimination and in regular algebra, the y terms will go away, and then I'll be left with a differential equation where, the only unknown dependent variable is x, right, and x depends on t. So I'd be left with this, d times d minus 2, and then plus 1, right, that operator applied to x, and then no y's equals 0. And what I'm going to do now is solve, find the general solution to this equation, right? Find what x sub t could possibly be. Okay. Well, this operator here is actually, d squared minus 2d plus 1 times x equals 0. And this actually is nice and factorable here. This is d minus 1 squared times x equals 0. And hopefully you recall annihilators. If not, this equation here is the same as, taking this down here, y, x double prime minus 2x prime plus x equals 0. You have this equation with constant coefficients, and then if you wanted, you could let x equal e to the mt. Remember, t is the independent variable here. And then you get the auxiliary equation, m squared minus 2m plus 1 equals 0, and you get the roots m equals 1. But it's a repeated root, right? It's a repeated root. So our general solution to this equation here, x sub t, equals, some constant, say c1 times e to the t, and hopefully you remember what happens with a repeated root, plus some constant c2 times, t e to the t. All right, now this is only, we're not done. Right? This is just a solution of that equation, in terms of x. So now going back, all right, let's go back to the, so I found some general solution for x, but we need y as well. Pardon me. So going back to the, again, the way the system looked when I got all the x's and y's to the same side. Well, that was eliminating y. Now suppose I want to eliminate x. All right, so if I want to eliminate x, I got to do some different operations to these equations. All right, so let's just clear that out. We'll come back to that. All right, so if I want to eliminate x, well, this has the operator d minus 2 in front of it. This has a minus in front of it, so it just needs the operator d minus 2, and then they'll be opposites. So all I'm doing down here is applying the operator d minus 2 to everything. All right? So that'll give me the following system, equivalent system. So I'd have, d minus 2 applied to x plus y equals 0. And then the opposite of d minus 2 applied to x plus d times d minus 2 applied to y. Right. Again, doing this to every term. And then d minus 2 applied to 0 would just still be 0, right? That's the derivative of 0 is 0, minus 2 times 0 would be 0. So still 0 on that other side. And then just as before, now I have what I want, so I can eliminate x, right? These operators in front of x are opposites. So now I add the equations, and we get an equation in y. We have, d times d minus 2 plus 1 applied to y equals 0. And this is the exact same looking equation as I had earlier with x, right? D times d minus 2 plus 1 applied to x equals 0. Now there I had constants c1 and c2 show up. Since this looks exactly the same, we're going to have y of t equals, now don't use the same constants, right? This is a totally different function, right? The x and y are different. So the general solution of this equation is, some other constant, c3, right? Something different, c3 times e to the t plus some other constant, c4 times t times e to the t. Right? And so here's like another half of the solution. Now you got to be careful. These constants are tricky. All right. You might think, oh, well, there, I found the two functions. These are the solutions. This x of t and y of t that I've just described is not a solution of the system for any choice of the constants. Is not a solution of the system for any choice or every choice of C1, C2, C3, and C4. All right, and I'll show you. All right, I'll show you. So what we need to do next, all right, after finding the general, what the general x looks like, what the general y looks like, then we have to determine how do I choose these constants then, right? If I can't choose them to be whatever I want, how do I choose the constants? So the big question now, what we're going to try to find is, what is the relationship between these constants, C1, C2, C3, and C4? Or what are the relationships? So what is the relationship or relationships between the constants? How would I choose them in order to get actual solutions to the system? Okay. So this is where some substitution comes into play. All right, we're going to go back to I'll go back to my differential equation here. Or sorry, my system of differential equations. And again, we had the following, right? X of t was, I said, c1 e to the t plus c2 times t e to the t. And then y of t was c3 e to the t plus c4 t e to the t. Right, and then all I need to do is, find the first derivative of these with respect to t. Right, that's all these are saying. So dx dt, right, that would just be c1 times e to the t plus, and then for this next term, I'd use the product rule. So it would be c2 times t e to the t plus c2 e to the t. And I guess I could combine the e to the t's here and get c1 plus c2 e to the t, then plus c2 times t e to the t. All right, so there's the first derivative of x with respect to y, and the first derivative of y with respect to t, and then the first derivative of y with respect to t would be the same thing, but instead of c1 and c2, I have c3 and c4. Right. So that'd be c3 plus c4 times e to the t plus c4 times t e to the t. All right, so putting these in, picking, say the first equation. Let's say we sub into the first equation. We'd have c1 plus c2 times e to the t plus c2 times t e to the t must be equal to 2 times x, so 2 times how x looks, so that would be, just distributing the 2, that would be 2c1 e to the t plus 2c2 t e to the t, right? And then minus y, so minus all this, right? So minus c3 e to the t minus c4 t e to the t. And what I'm going to do is I'm going to take everything to one side and have 0 on the other, and we'll see very clearly how these coefficients have to relate to one another. So if I put all the e to the t terms together, so I'd subtract 2c1, right, so c1 minus, that would be negative c1. Now you got the plus c2 still, and then I'd add c3, right, so plus c3 times e to the t. That's all the e to the t terms put together. Plus, and then all the t e to the t terms. I have c2, and then minus 2c2, and then plus c4. So negative c2 plus c4 t e to the t. And in order for this to be all, when I take everything to one side, 0 on the other, the only way this is going to be equal to 0 for any t is if the coefficients are 0, right? So if negative c1 plus c2 plus c3, if that's equal to 0, and if negative c2 plus c4 is equal to 0. All right, what I'm going to try to do, so here are the relationships between the coefficients that I was talking about. Here's what determines relationships between coefficients. So it's this system here that determines how I can choose the coefficients and actually get a solution. Right? So what I mean by this is, I can't say, oh, let's have C1 be 1, that C2 be 2, C3 be 5, and C4 be 15. You can't just have them be whatever you want. You have to choose these coefficients, these 4 coefficients, so that these are satisfied. So if I had C1 be 1 and C2 be 1, then according to this, C3 would have to be 0. I can't choose whatever I want for C3. And then if C2 was 1, then I'd have C4 would have to be 1 as well. Okay, like these relationships have to hold. And so very often what you'll see when writing finally the general solution to the system is we'll try to express the coefficients of one of the part of the solution, say one function y, try to express the coefficients of one function in terms of the coefficients of the other. So can I get C3 in terms of C1 and C2? Yeah. According to this system here, C3 must be equal to C1 minus C2. And then C4, right, C4 must be equal to just C2. And then I make those replacements and we get our general solution to this system. So we have x sub t equals, those I'm keeping c1 times e to the t plus c2 times t e to the t. And, where I can choose c1 and c2 to be any constants I wish. Alright, but then once I've chosen these c1 and c2, the value of the constants, the value of the coefficients in the y function are determined. Y equals, c3 e to the t, but according to this, c3 is c1 minus c2. Plus, and then, c4 t e to the t, but according to this previous system of relationships, c4 is the same as c2 times t e to the t. And there you go. There's your general solution, the two functions that would satisfy both equations in the system at the same time. Because again, if you choose C1, C2, say you chose C1 to be 5 and C2 to be 3, well then C3 must be 2. If you don't pick if you didn't put 2 here, it would be not a solution. Okay? I've said it several times now, these relationships between the coefficients have to be satisfied in order for these functions to satisfy both equations of the system. Alright, so you gotta be careful. And like I said, very often to write the general solution, you're going to try to express the coefficients of one function in terms of the coefficients of the other one. And try to limit it to as few constants, as few choices as possible. Right? So hopefully that made sense. Now if you want to verify this, if you want to verify that this is indeed a solution, no matter what you choose for C1 and C2, take the derivative of this, and then put 2 times this minus this, and the first equation should be true. And then take the derivative of y, put it here, and then put x here, and then the second equation should be true as well. And again, I'll leave that to you. Alright, but I think the trickiest part is working with the coefficients, working with the constants. Because again, certain relationships, basically you're just substituting back into one of the equations and establishing what relationships do the constants need to have in order for our pair of functions to actually be a solution to the system. I hope that makes sense. Okay. Now if it doesn't, I'm going to be doing this again. Right, I got a couple more examples. Alright, so this next example is what they would call a non-homogeneous system. Right? If you recall from the first example, when I took everything to one side, there was nothing but zeros on the other side. There were no terms that solely depended on t and t alone, the independent variable. Here we have a couple terms that actually depend on the independent variable by itself, independent variable t. So this would be considered a non-homogeneous system, but again, I'm not really going to write that down. Now don't forget, I'm going to do this. Remember, D is a differential operator. It represents the derivative with respect to time, or not time, but t. Usually t could be representing time. And then I'll take all the the dependent variables to one side and keep the independent variable terms with t on the other. And so if I write with the differential operator and do that, we'll have the following. We'll have d applied to x, right, plus y equals t, right, leaving the terms dependent, that are expressions of only the independent variable on the other side. And then we have we have d applied to y here, right? And I'm subtracting x, and then we have negative t on the other side. Right. Okay. So I got the same setup kind of like in the first example, right? My x's and y's, my dependent variables lined up on one side, independent variable stuff lined up on the other. And I think an easy thing to get rid of here would be x. All right, so I'm going to eliminate x by doing the following. To this first equation, I would simply multiply by negative 1. Multiply by negative 1. And to this second equation, I'm going to apply the differential operator d. You know what? Nope. How about this? Don't do anything to the first equation. I was thinking of y for some reason. My apologies. So I'm not going to do anything to the first equation. Leave it as dx, and then just put a d in front of this, and that way there'll be minus dx, and there'll be opposites. My apologies. So I'm going to apply the differential operator d, right, which is the derivative with respect to t, to everything on this second equation. All right, so if I do that, we have the following. Didn't do anything to the first equation, so dx plus y equals t. And then we have minus, dx, right, applying d to that, plus d squared y, so the second derivative of y with respect to t, equals, and then again, d applied to this, the derivative of negative t with respect to t would be negative 1. So I hope you see why that's negative 1. All right, now I have what I want, these operators in front of the x are opposites. Then we add the equations together to eliminate the x terms. And we get a differential equation in y with d squared plus 1 as the operator. D squared plus 1 as the operator on y. And then it's a non-homogeneous equation. Over here I'd have t minus 1. So hopefully you recall how to solve non-homogeneous equations, either with the annihilator method or superposition approach. But first I'll look at the associated homogeneous equation. And again, this would be the same as y double prime plus y equals t minus 1, right, where t is the independent variable. It's the same as that. So the associated homogeneous equation looks like the following: y double prime plus y equals 0. And you have an equation with constant coefficients, so we let y equal e to the mt. That'll give me this auxiliary equation, right? M squared plus 1 equals 0. The roots are plus or minus I. And so that complementary function, right, yc, the solution of the associated homogeneous, is some constant, say c1, times the cosine of t, plus some other constant, c2, times the sine of t, right? All right, and then based on annihilators, if you remember annihilator stuff, or undetermined coefficients with the superposition principle, d squared would annihilate this. And so we'd have the form that our particular solution takes, yp, the form a particular solution to this takes would be some constant plus some constant times t, a plus bt. All right. So I put this in. All right, I put this into the yp prime would be just b, yp double prime would be 0. So all we'd have here is a plus bt equals -1 plus t minus 1. So a must be -1, b must be +1. So the particular solution I'm looking for is t minus 1. All right, so after all that, you can put the general solution together for this differential equation involving y. So y of t will take on the following form. Your complementary function some constant c1 times the cosine of t plus some constant c2 times the sine of t plus the particular solution t minus 1. Right, so this is what y looks like. All right. So now I'm going to do the same thing for x. All right, so maybe I'll box this up. All right, this is only half the solution. Again, c1 and c2 are constants, and let's do the same thing for x. All right. So go back to the way the system looked earlier, written in differential notation, right, with differential operators. And now I'm going to eliminate y. Now in order to do that, sorry about this, scratching some stuff off, I'll keep this as, well, I'll apply d to the first equation. I get dy, and then just multiply one of them by -1, maybe the second equation by -1. All right, so let's see what that changes the system into. All right, so if I go back and eliminate y, we'll do those two applications. We have d squared x, right, the second derivative of x with respect to t, plus dy equals 1. Remember, d is the derivative with respect to t. The derivative of t is 1. And then we have times -1 down here, so x minus dy equals t. Now I've got the opposite operators on y's. We add the equations to eliminate y, and that gives me the following differential equation: d squared plus 1 operating on x equals t plus 1. All right, now this is very similar to the equation I just had with y. All right, this equation here, but instead of t minus 1, it's t plus 1. So I'll leave it to you. Okay, I will leave it to you to show that x of t is going to look like the following. Now again, these are different constants, okay? Say c3, because I already had c1 and c2. Right? I already had c1 and c2 in my solution for y. c3 times the cosine of t plus c4 times the sine of t. And again, I promise you that the particular solution in question here would be t plus 1 plus t plus 1. All right. So we have the way our solution looks. All right. We know what x needs to look like. We know what y needs to look like, all right, from this page. So we know what our solution to the system needs to look like. But then comes the question, what are the relationships between these constants, these c1, c2, c3, and c4? Because as before, as in the first example, you can't just replace these with 1, 2, 3, and 4, or 5, 7, 11, and pi. You can't just replace all 4 of them with whatever you want and still have a valid solution to the system. So we need to figure out relationships between the constants, right? So after finding the way the solution needs to look, then, as with the first example, we need to find relationships between the constants. And this is just by substituting back into one of the equations from earlier, one of the equations from the system. Okay. So going back to the system, well, first let me write out what, we have x, we have y. Let me just tell you right now that dx dt would be, negative c3 sine t, right, plus c4 cosine t, and then plus 1, right? And dy dt would basically be the same, right? It would be negative c1 sine t plus c2 cosine t plus 1, right? So negative c1 sine of t plus c2 cosine of t plus 1, right? And then going back to the system, right, here was the system that we started with, right there. And I'll sub this stuff in along with x and y. Let's just go into I'll just go into the first equation again. All right, so in the first equation, because it really shouldn't matter, you'll get the same relationships no matter what equation you go into, because this pair of functions should satisfy both equations when you're done setting them up. So we have dx dt, so negative c3 sine of t plus c4 cosine of t plus 1 equals the opposite of y. Remember, y looks like this. Okay, so the opposite of this, so minus 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 plus, right? So equals negative c1 cosine t minus c2 sine of t minus t plus 1, and then plus t. Alright, then we got the plus t. So dx dt, left side, equals the opposite of y, and then plus t. And then just as before, I'm going to take everything to one side, 0 on the other, and we'll be able to hopefully easily see then the relationships between the constants. So let's take all the sine terms together. We'd have c2 minus c3 times sine of t. Let's look at the cosine terms. Plus c1 plus c4 cosine of t. And then you can see that the t's are going negative t plus t. Subtract 1 from both sides, and so we equals 0. Right. And again, the only way this is going to be equal to 0 for any t is if these coefficients are 0. So here are the relationships. Right, here are the relationships between the coefficients, between these constants. Right, so c2 minus c3 must be equal to 0, and c1 minus plus c4 must be equal to 0. Right. So again, you can't just pick whatever here's the way the solution looks. But again, there's x and y. But again, you can't just pick whatever you want for all four constants. If I have c1 is 0, if I pick whatever I pick for c2 must be the same as what I pick for c3, right? According to this relationship, c2 must be equal to c3. And whatever I pick for c1 must be the opposite of what I pick for C4. So again, it can't be like 5, 7, 9, 13. You can't just let them be whatever you want. If C2 is 5, C3 must be 5. If C1 is 10, C4 must be negative 10. Right? In order for these to actually be a solution to this system to satisfy both equations. All right, so as before, as in the first example, I'm just going to rewrite one of these functions constants in terms of the other ones. So I'm going to replace C3 with C2, and I'll replace C4 with negative C1. All right, so the general solution then to our system looks like the following. So x of t equals, again, C3 I'm just going to replace with C2. So C2 times the cosine of t. And then C4 I'm going to replace with negative C1. So minus C1 times the sine of t, and then plus t plus 1. And then y, I'll leave the coefficients of y the way they are. Well, C1 times the cosine of t plus C2 times the sine of t plus t minus 1. And there you go. There's the way the general solution to this system works. And again, you can verify this by taking the derivatives with respect to t and then plugging these into both equations of the original system, and both equations should be true. It should satisfy both of them. All right, but you gotta have these relationships though, right? You can't just throw out whatever constants you wish willy-nilly, because you're not always going to have a valid solution. If you picked C1, C2, C3, and C4 to be like 5, 7, 9, and 11, that wouldn't be a solution to the system. Right? The coefficients you pick have to satisfy certain relationships to be actually a solution of the given system. Okay. Wonderful. All right, so I know I said in the beginning I was going to do 3 examples, but this is already 40-some minutes long, and I think you get it. I did a non-homogeneous example. I did a homogeneous example. Now, of course, the differential operators could be of higher order, right? The highest order we saw here was up to order 2 for some of these differential equations. But just know that when you apply some operators and do elimination, the resulting equation could be an order higher than 2. Just know that. And you go about the same procedure though. Eliminate one variable, find what the other one looks like. Then do the opposite, eliminate the other variable, and solve the resulting differential equation to find what the other variable needs to look like, the other function. But then once you find what both functions look like, you then have to show what are the relationships between the constants, the coefficients, the C1, C2, C3, C4, C5, whatever they are. Because those relationships need to be established in order to have a valid solution to the system, right? You can't just choose whatever you want for any constant. Right? They need to satisfy certain relationships, as I've said many times now. Alright, so hopefully watching me go over these couple examples help you out when you're solving systems of differential equations through systematic elimination on your own. And thank you very much for watching.